6570. If an aircraft has negative dynamic and positive static stability, this will result in A. Undamped oscillations, B. Divergent oscillations, C. Convergent oscillations. The correct answer is B. If an aircraft has negative dynamic stability and positive static stability, it will result in divergent oscillations. Let's break down the reasoning. Negative dynamic stability refers to a condition where the aircraft's response to a disturbance amplifies over time. In this case, when the aircraft is disturbed from its equilibrium state, the resulting motion will continue to grow larger and larger with each cycle. This indicates an unstable behavior where the aircraft's motion diverges from its original position. Positive static stability, on the other hand, indicates that the aircraft has a natural tendency to return to its original position after being disturbed. The restoring forces within the aircraft are greater than the destabilizing forces, resulting in a stable equilibrium. When an aircraft possesses negative dynamic stability and positive static stability, the restoring forces are not strong enough to overcome the destabilizing forces over time. As a result, the disturbances introduced to the aircraft's motion will cause the oscillations to continually increase in magnitude, leading to divergent motion away from the equilibrium state. In summary, an aircraft with negative dynamic stability and positive static stability will experience divergent oscillations. The disturbances introduced to the aircraft's motion will cause the oscillations to grow larger and larger with each cycle, indicating an unstable behavior. 6506. An airplane would have a tendency to nose up and have an inherent tendency to enter a stalled condition when the center of pressure is A. Below the center of gravity, B. Aft of the center of gravity, C. Forward of the center of gravity. The correct answer is C. An airplane would have a tendency to nose up and have an inherent tendency to enter a stalled condition when the center of pressure is forward of the center of gravity. When the center of pressure is located forward of the center of gravity, it creates a destabilizing effect on the airplane. This configuration leads to an increased nose-up pitching moment, which can result in an upward rotation of the aircraft. The center of pressure represents the point at which the total aerodynamic force acts on the aircraft. It is typically located near the wings, where the lift force is generated. The center of gravity, on the other hand, represents the point at which the total weight of the aircraft is concentrated. In a typical aircraft, it is desirable to have the center of pressure located slightly aft of the center of gravity. This configuration provides stability and helps maintain the aircraft in a properly trimmed state during normal flight conditions. However, when the center of pressure is positioned forward of the center of gravity, it creates a destabilizing effect. An increase in lift or an upward force acting at the center of pressure tends to rotate the aircraft nose up, making it more prone to entering a stalled condition. A stalled condition occurs when the airflow over the wings becomes disrupted, resulting in a loss of lift and an increase in drag. When the center of pressure is forward of the center of gravity, it can exacerbate the tendency for the aircraft to enter a stalled condition. In summary, when the center of pressure is forward of the center of gravity, an airplane has a tendency to nose up and is more likely to enter a stalled condition. The forward positioning of the center of pressure creates a destabilizing effect, leading to an increased nose-up moment. 6576. A swept-wing airplane with weak static directional stability and increased dihedral causes an increase in A. Mach tuck tendency, B. Dutch roll tendency, C. Longitudinal stability. The correct answer is B. The reasoning behind this swept-wing configuration, a swept-wing design refers to an airplane's wings that are angled backward from the root towards the wingtip. Swept wings are commonly used in high-speed aircraft to reduce drag and improve performance at higher speeds. Static directional stability. Directional stability refers to an aircraft's inherent tendency to maintain its intended direction of flight without the need for constant pilot input. Static directional stability specifically relates to the initial response of the aircraft when disturbed from its intended course. Weak static directional stability. Weak static directional stability means that the aircraft has a reduced or inadequate tendency to naturally maintain its intended direction of flight. It implies that the aircraft's stability characteristics are not strong enough to counteract disturbances and maintain straight and level flight. Dihedral effect. Dihedral refers to the upward angle of the wings when viewed from the front or top of the aircraft. Increased dihedral means that the wings have a more pronounced upward angle. Considering these factors, when a swept-wing aircraft has weak static directional stability and increased dihedral, it leads to an increase in Dutch roll tendency. Here's the detailed reasoning. Dutch roll is a lateral/yawing oscillatory motion of an aircraft characterized by a combination of rolling and yawing motions. It is typically an undesirable characteristic that can occur in aircraft. Swept-wing effect. The swept-wing configuration can introduce a destabilizing effect on the aircraft's yawing motion. The swept wings tend to generate a yawing moment that can cause the aircraft to yaw or oscillate side to side. Weak static directional stability. The weak static directional stability exacerbates the yawing motion induced by the swept wings. It means that the aircraft has a reduced tendency to naturally counteract yawing disturbances and maintain a straight course. Increased dihedral effect. The increased dihedral contributes to the Dutch roll tendency. The dihedral effect causes the wings to generate a rolling moment when the aircraft yaws. This rolling moment combines with the yawing motion induced by the swept wings, resulting in the characteristic rolling and yawing oscillations of Dutch roll. In summary, when a swept-wing aircraft has weak static directional stability and increased dihedral, it increases the tendency for Dutch roll. The combination of the destabilizing swept-wing effect, weak static directional stability, and increased dihedral leads to lateral/yawing oscillations characterized by rolling and yawing motions. 6531. Changes in the center of pressure of a wing affect the aircraft's A. Lift/drag ratio. B. Lifting capacity. C. Aerodynamic balance and controllability. The correct answer is C. The center of pressure, COP, is the point on the wing where the total aerodynamic force is considered to act. It represents the average location of the lift force acting on the wing. The position of the center of pressure can change based on various factors, such as angle of attack, airspeed, and configuration changes. Aerodynamic balance refers to the distribution of forces and moments on an aircraft, which affects its stability. Controllability refers to the ability of the pilot to control and maneuver the aircraft. Here's how changes in the center of pressure affect aerodynamic balance and controllability. Aerodynamic balance. The position of the center of pressure affects the distribution of forces acting on the aircraft. When the center of pressure shifts, it can change the balance of lift and other aerodynamic forces acting on the aircraft. This, in turn, affects the aircraft's stability and trim. Stability. The position of the center of pressure relative to the center of gravity, COG, determines the stability characteristics of the aircraft. Changes in the center of pressure can alter the longitudinal, pitching, stability, lateral, rolling, stability, and directional, yawing, stability of the aircraft. These stability characteristics are crucial for maintaining the aircraft's desired flight path and attitude. Controllability. The position of the center of pressure also influences the controllability of the aircraft. Control surfaces, such as ailerons, elevators, and rudder, are used by the pilot to maneuver the aircraft. Changes in the center of pressure can affect the effectiveness and responsiveness of these control surfaces. A well-balanced and controllable aircraft requires proper coordination of the center of pressure with the control surfaces. In summary, changes in the center of pressure of a wing affect the aircraft's aerodynamic balance and controllability. The position of the center of pressure influences the distribution of forces, stability characteristics, and the effectiveness of control surfaces. Proper aerodynamic balance and control are essential for safe and maneuverable flight. 6575. The purpose of aircraft wing dihedral angle is to A. Increase lateral stability. B. Increase longitudinal stability. C. Increase lift coefficient of the wing. The correct answer is A. Dihedral refers to the upward angle formed between the wings of an aircraft when viewed from the front or top. It is a design feature where the wings are angled upwards to create a V shape. The dihedral angle plays a significant role in the lateral stability of an aircraft. Here's how it increases lateral stability. Lateral stability. Lateral stability refers to the aircraft's ability to resist rolling or maintain its wings level when subjected to lateral disturbances, such as gusts or side slip. It is crucial for maintaining coordinated flight and preventing uncontrollable rolling motions. Dihedral effect. The dihedral angle contributes to the lateral stability of an aircraft. When an aircraft with dihedral experiences a side slip or rolling motion, the dihedral effect comes into play. Roll due to side slip. When the aircraft experiences a side slip, with one wing lower and the other wing higher, the dihedral angle creates a restoring force. The higher wing generates more lift due to its increased angle of attack, while the lower wing generates less lift. This difference in lift between the wings creates a rolling moment that tends to level the wings and reduce the side slip. Roll due to gusts. When the aircraft encounters a gust from the side, the dihedral effect also helps in restoring the aircraft to its level position. The gust creates an asymmetrical lift distribution, with higher lift on the lower wing. This generates a rolling moment that counteracts the gust-induced roll and brings the wings back to level. By incorporating dihedral into the wing design, the aircraft benefits from the dihedral effect, which increases lateral stability. The upward angle of the wings allows for a more pronounced rolling moment to counteract disturbances and maintain level flight. It's worth noting that dihedral primarily influences lateral stability rather than longitudinal stability or the lift coefficient of the wing. In summary, the purpose of aircraft wing dihedral angle is to increase lateral stability. The dihedral effect helps the aircraft resist rolling motions caused by side slip or gusts, promoting stable and coordinated flight.